press the bell icon on the YouTube app and never miss another update.
Good morning, students. In the previous class, we have discussed two important concepts. Number one, relation between phase difference and path difference, and number two, intensity of a wave, right? So, intensity of a wave is a measure of average energy transported per second per unit area by a wave, right? Now, the intensity by definition, we have I is equal to P by A, where P is the power of the source. For example, when we take an electric lamp, it is having power 60 watt, 100 watt, 1000 watt, right, depending upon the requirement. When we see a speaker, right, again it has the power 25 watt speaker, 30 watt speaker, 50 watt speaker, etc., right, that indicates the energy emitted per second, right. And here, as the area increases, right, the intensity also decreases, right. So when I am speaking, right, now a person in front of me can hear me loudly, but a person far away from me, we cannot able to hear the sound. It is because, right, as distance between the speaker and the listener increases, right, now the intensity goes on decreases. Suppose if we have a point source, say we have a point source. Suppose there is a person at a distance P1. Now the sound spreads over the entire area, right, of spherical surface of radius R1 with the source as center, right. So in this case, the intensity I1 is equal to P by A1, that is equal to P by 4 pi R1 square. Suppose we have another person who is at a distance R2 from the source, right. Now, this sound while reaching P1, it spreads over a sphere of radius R2. Now in this case, the intensity for the person P2, it is P by 4 pi R2 square, right. Or in general, we can write intensity of a wave is inversely proportional to square of the distance between the source of the wave and the observer or receiver, right. So this is this equation is used when we have a very small source, point source, right, in which the energy, right, spreads over a sphere. If the source is an extended source, then that I is equal to, right, P by R square. This is for extended source, and this is the expression for, right, the point source, right. And intensity is also given by the expression, right, I is equal to 2 pi square A square F square V into rho, where A is amplitude, F is frequency, V is velocity, and rho is density of the medium, right. Now we will consider another concept, that is a principle of superposition of waves. This principle of superposition of waves, Now, let me write the statement, then I will explain it to you. Now, it states that, right, right. Now it states that the resultant displacement of a particle of medium due to superposition of two or more waves, right, traveling in the same direction is the vector sum of individual displacements of the waves, right. Now that means, so whenever a single wave represented by y1, right, is propagating through a medium, so any given particle, right, has a displacement y1 at any instant of time t1. Suppose another wave y2 is propagating through a medium separately, again at any given instant of time a particle will have a displacement y2. So when these two waves, right, y1 and y2, right, are propagating through a medium, right, simultaneously in the same direction, they overlap on each other, then the displacement of a particle at any instant of time is y. Then the displacement, resultant displacement, right, y is equal to, it is y1 plus y2, where y1 is the displacement of the first wave and y2 is the displacement of the second wave, right. Now suppose this is y1 is equal to 3 centimeter, y2 is equal to 5 centimeter, right. Then when y1 alone is propagating through the medium, the displacement at any instant of time is 3 centimeter, right, for a given particle. When y2 alone is propagating through a medium, then displacement of a particular particle is 5 centimeter. When they superpose on each other, then the resultant displacement may be y is equal to, I am talking about the magnitude of displacement, so y1 plus or minus y2. So y1 may be y1 plus y2 or y may be, right, y1 minus y2, right. y1 minus y2 means the difference between the two waves. In this case, this is 3 plus 7, 8 centimeter. In this case, 3 minus 5, that is minus 2. Actually, it is 2 centimeter, right. So the displacement may be 8 centimeter, displacement may be 2 centimeter, or it may have any value between 2 centimeter and 8 centimeter. That depends upon, right, the path difference and the phase difference between the two waves arriving at a point, right. Now here when we consider wave y1 with origin O, and I have taken the transverse wave, it consists of crest and trough, and if I take longitudinal wave, it consists of alternate compressions and rarefaction. Now this is now if I take another wave like this, so with origin O dash and the crest and trough, right. So when we say the phase difference between two particles, now it is the distance between the two particles, right. Mean the phase difference between two particles of propagating medium separated by certain distance due to a single wave. But when we are considering phase difference between the two waves, it is the taken at the origin, we will say same point. So this is O, I mean 0, this is also 0. The phase difference between the two waves is 0, right. When phase difference between the two waves is 0, right, then the principle of superposition takes place like this. So here the crest of one wave falls over the crest of the other wave, and trough of one wave falls over the trough of the other wave. So here the direction of displacement is same in both the cases, right, and the resultant displacement y is equal to y1 plus y2, right. Now we say that the two waves are interfered constructively, and this is called constructive interference. This is called constructive interference, right. So in this case, right, resultant displacement y increases, resultant amplitude increases, and resultant intensity increases here, right. So when phase difference between the two waves is equal to 0, right, then the interference is said to be constructive interference. When constructive interference takes place, crest of one wave falls over crest of the other wave, and trough of one wave falls over the trough of the other wave, right. So in case of longitudinal waves, compression of one wave falls over compression of the other wave, and rarefaction of one wave falls over rarefaction of the other wave, right. Now again, now suppose if the wave arrives like this, this is O dash, this is y2. Now here the phase of this wave is 0, and the corresponding point has a phase difference, phase of phi. Now the phase difference between these two waves y1 and y2, that phi is equal to pi. When these two waves overlap on each other, it takes place like that. So trough of one wave falls over the crest of the other wave, and crest of one wave falls over the trough of the other wave. In this case, we see the displacements of the two particles are exactly in opposite direction. So, in this case, the resultant displacement y is equal to y1 minus y2 or y2 minus y1. Now, we say that the two waves are interfered destructively, and this phenomenon is called destructive interference. This phenomenon is called destructive interference. Right? When destructive interference takes place, here the resultant displacement decreases, the resultant amplitude also decreases, and the resultant intensity also decreases. Right? So, when destructive interference takes place, the resultant displacement, resultant amplitude, and resultant intensity decreases. Right? So, this is destructive interference. Right. Now, suppose if the second wave is arriving at the point like this, right, this is O dash. Now, the corresponding point in the first wave has a phase of 2 pi. So, in this case, the phase difference phi is equal to 2 pi. When phase difference phi is equal to 2 pi, again the constructive interference takes place. That means crest of one wave falls over the trough of the other wave. Right. Now, at some point, if the wave arrives like this, now this corresponding point has a phase of 3 pi. Now it has a phase of 0. Now the phase difference is 3 pi. See what happens here. Again, trough falls over crest and crest falls over trough. That means destructive interference takes place, right? So, when two waves propagating through a medium are superposed on each other, then constructive interference takes place at certain points and destructive interference takes place at certain other point. Therefore, at some points intensity or energy distribution increases, and at some points intensity or energy distribution decreases. This is the result of the superposition of two waves. When two or more waves traveling through a medium superposed on one another, then in the propagating medium the energy will be more at certain points and energy will be less at certain points, right? Now here, when constructive interference takes place, the phase difference phi is equal to 0, 2 pi, 4 pi, 6 pi, etc. In general, it is 2n pi, where n is equal to 0, 1, 2, 3, etc. an integer. You put n is equal to 0, we get 0. We put n is equal to 1, we get 2 pi. When we put n is equal to 2, right, we get 4 pi, etc. So, when phase difference is 0 and even pi, constructive interference takes place, resultant displacement, amplitude and intensity all increase. So, when destructive interference takes place. When destructive interference takes place, the phase difference phi is equal to pi, 3 pi, 5 pi, 7 pi, etc. in general, right? It is a 2n plus 1 pi. That means again here n is an integer 0, 1, 2, 3, etc. When we put n is equal to 0 here, we get pi. When we put n is equal to 1, we get 3 pi. When we put n is equal to 2, we get 5 pi and so on. So, when the phase difference between two waves arriving at a point where the superposition takes place is pi, 3 pi, 5 pi, 7 pi, in general 2n plus 1 pi, right? Destructive interference takes place and the intensity decreases at that point, right? Now, you might have heard a kind of music called beats, right? Beats is produced due to superposition of two sound waves of slightly different frequency traveling in the same direction. In that case, in beats, we don't hear the continuous sound. At one moment we will hear a maximum sound, next moment no sound, third moment, right, a maximum sound. So the maximum and minimum sounds, right, of intensity sounds, right, they occur, right, alternately with respect to time, right. This phenomenon is called as beats. We will discuss the beats when we are discussing about the sound, right. So the formation of beats due to superposition of two sound waves and formation of stationary wave due to superposition of two identical progressive waves traveling in opposite direction can be explained on the basis of the principle of superposition of waves, right. In general, both the phenomena exhibited by waves, interference of waves and diffraction of waves, can be, right, explained on the basis of the principle of superposition of waves. Remember the condition for constructive interference and the condition for destructive interference, right. Now, let us consider waves around us, right. In our day-to-day life, we come across so many kinds of waves like light wave, sound wave, microwave, radio wave, seismic wave, etc. Though they have right different sources of production and properties, but all of them transport energy from one point to another point, right. Now we will take the light wave. So number one, so light is produced, right, due to transition of atom, right, from higher energy orbit to lower energy orbit in an excited atom, right. Now light is emitted due to transition of electrons from higher energy orbit to lower energy orbit. We know that an atom consists of a central nucleus and electrons are revolving around the nucleus in various atoms. Suppose if E1 is the energy of lower orbit and E2 is the energy of higher orbit, when external energy is supplied to an atom, for example by heating it, the electron in the lower orbit takes the energy and jumps to a higher energy orbit. Now the atom is said to be in excited state. An atom cannot lie in excited state for a long time. In a very short interval of time, about 10 to the power of minus 8 second, the electron will come back to its lower energy state. Now in this case the energy difference E2 minus E1 is emitted as that light. According to Planck's quantum theory, energy associated with light particle photon is E is equal to h nu. So number 2, light is a form of energy. Light is a form of energy that causes sensation of vision. Light is a form of energy that causes sensation of vision. Now the third one, light is electromagnetic transverse wave. Now the fourth one, light travels with a speed of c is equal to 3 into 10 to the power of 8 meter per second in vacuum. Now light has the highest speed in vacuum, and the speed of light is different in a different medium. Now the fifth property, so light exhibits dual nature. Light exhibits dual nature. It behaves as a particle as well as a wave. It behaves as a particle as well as a wave. Now when light is emitted from a source or absorbed by matter, it behaves as particle called quantum or photon. Photon is the name given by Einstein, and when propagating through a medium, light behaves as a wave. The phenomenon like interference, diffraction and polarization exhibited by light can only be explained by considering light as a wave. On the other hand, now the phenomena like photoelectric effect, Raman effect, the distribution of energy in a black body radiation, right, could be explained on the basis of the particle nature of light. That particle nature of light is called as photon. So whenever the atoms of a material body are excited such that the electrons will move from lower energy level to higher energy level, then the electron while coming back to lower energy level emits the light energy, and the eighth one, light waves, that what we call it as visible light, have a wavelength range from, right, 4000 into 10 power minus 8 meter to approximately 7800 into 10 to the power of minus 10 meter. That range is called right, visible light, right. Now again, all electromagnetic waves starting from gamma rays, right, next comes the X-rays, ultraviolet rays, light waves, infrared radiation, microwaves, radio waves, right, all are electromagnetic transverse wave, but among them the wavelength of electromagnetic wave less than 4000 into 10 power minus 10 meter, that is ultraviolet rays, X-rays and gamma rays are not visible. At the same time, the light electromagnetic waves of wavelength greater than 7800 into 10 to the power of minus 10 meter cannot be, right, seen, right. Now, right, sound waves. So number one, sound is produced by mechanical vibration in a material medium. So any vibrating body, right, in a material medium produces sound. For example, musical instruments, right. So musical instruments produced, right, musical sounds when they are set into vibration, right. Second one, again, sound is a form of energy that causes sensation of hearing. Now what is light? Light is a form of energy that causes a sensation of vision, and sound is a form of energy that causes sensation of hearing. Now the third one, right, sound, right, in air, particularly the large medium, right, is a mechanical longitudinal wave in air, because it is a mechanical wave, because it requires a material medium for its propagation. It is a longitudinal wave because it consists of a series of alternate compressions and rarefaction. Now at NTP in air, speed of sound is equal to 330 meter per second. Now speed of sound in air depends upon the temperature of the air at 0 degree Celsius, that is at NTP, normal temperature and pressure, the speed of sound is 330 meter per second and it is called 1 Mach. You might have heard of the speeds of missiles, right, war planes, right, etc., right, where they are moving with 1 Mach, 2 Mach, 3 Mach. Nowadays, right, there are some missiles, right, which are supposed to be moving at a speed of 17 to 20 Mach, right. 1 Mach means 330 meter per second. And the fifth one, so sound waves of all frequencies cannot be heard by the normal human ear. A normal human ear can hear only the sound waves from, right, 20 hertz to, right, 20,000 hertz, right. So these sounds are called audible sound. The wavelength of sound less than 20 hertz are called infrasonics, right. Dolphins, dogs and are sensitive to, right, infrasonic, and the sound waves of frequencies, I mean it's not wavelength, sorry, this is frequency. Now generally the range of visible light is expressed in wavelength and the range of the audible sound is expressed in terms of frequency. So frequency from 20 hertz to 20,000 hertz, right, are audible sound, and frequencies greater than 20,000 are called, right, ultrasonics, right, and ultrasonics are used in sonar, right. Now the sixth one, right, velocity of sound in a material medium depends upon the property of medium like elastic property and density. So in general, velocity of sound in solid is greater than velocity of sound in liquid, which is greater than velocity of sound in gas. It is because elasticity of solid is greater than elasticity of liquid, which is greater than elasticity of gas, right. So again, apart from this, the velocity of sound in a material medium depends upon the properties like elastic property and the mechanical property. Again, we are having microwaves and radio waves. Microwaves and radio waves both are electromagnetic waves, right. Microwaves have a wavelength range from 1 millimeter to, right, 5 centimeter, right. They can be focused up, right, as a beam. They are used in microwave ovens and in radar system, right. They are also used for short range communication purpose. Radio waves are again, right, electromagnetic waves of wavelength range from 1 meter to 5,000 meter. They are used in radio communication purposes, right. Both microwaves and radio waves are produced by oscillating charges or accelerated charged particle, right. And that completes this chapter, waves, and in the next class we will discuss some numerical problems, right. Okay, thank you very much.